Hello everyone. In this video, we're going to be solving an exponential logarithmic equation. Maybe both, right? We have x to the power ln x equals ex, and we're going to be solving for x values. Ln x is used for natural log. Unfortunately, I've seen Wolfram Alpha and some textbooks using log log for base e, which is the natural log. Anyways, I use ln for natural log. Just wanted to let you know so there's no confusion. I'll be presenting two methods, and let's start with the first one. For my first method, I want to go ahead and natural log both sides because we can. Now, there's a couple ways to approach this problem. You can use the natural log on both sides, which makes a lot of sense, or you could use another base. You could even use base x if you want, or base 10, which is log. So I usually use log for base 10. So log x would mean log x with base 10, and ln x would be log x with base e. E is Euler's number, by the way, and Euler is just amazing, right? Anyways, if you like Euler's number and some identities associated with it, then you can go ahead and check out my other channel, which is aplusbi, where I go over problems in complex numbers. I also made lecture videos if you're new to complex numbers. Anyways, so to be able to solve this problem, I'm going to use the natural log because it's in the exponent, and that will make things a lot easier. So let's go ahead and ln. Oh, no, also the presence of e on the right-hand side actually kind of like an icing on the cake makes it even better. So let's go ahead and ln both sides. And when we do, we kind of need to follow the properties of logarithms. What are they? Let's just quickly talk about properties. We have three main properties. One of them is the product. So if you have ln of a product, that can be written as the ln of the sum of two ln's. If you have a quotient, then you can basically turn it into subtraction. And finally, if you have a power, which is repeated multiplication in this case, then you can bring that power to the front and make it a coefficient. Make sense? So we're going to be using two of those properties, the first one and the third one right now. Let's go ahead and take a look at this, for example. This looks like a power of x, right? Because when you have something like this, you also have to be careful. This one is definitely different from this one. They're not the same, right? Because here the base is ln x, the exponent is ln x. Here, ln x is an exponent, but it's only for x, and then log is applied afterwards. So you got to be very careful with these things, and it's why sometimes it's important to use parentheses, but I generally do not use parentheses, and I think Wolfram Alpha or Desmos is not going to let you type up something like this. Anyways, move the ln x to the front. You're going to get something like ln x times ln x, because that's the power, equals, here we can apply the first property, which is the product property, and write it like this. And now notice that ln x is repeated, so that is ln x squared, right? And then ln e is 1, because remember, that is log e with base e, so that will be 1 by definition, and this is just ln x. Now, what does this tell you? It tells you substitute, right? If it doesn't, I'm sorry, I don't know what to say, but this definitely calls for substitution. You can definitely make it a quadratic in ln x, but I'd like to use substitution. It's easier. So let's go ahead and call this something. How about u? Okay. If ln x is equal to u, then we get, or you get, u squared equals 1 plus u. Obviously, this is quadratic. Let's put everything on the same side and then solve the resulting quadratic equation. Do you smell the golden ratio, or at least some type of, or maybe a flavor of golden ratio? I hope you do. From here, we're going to get u equals negative b plus minus the square root of b squared, 1 minus 4ac, which is plus 4, which is 5. There you go. Here's your golden ratio. You got it? Okay. What is u though? U is, you are not. U is ln x, right? So we're going to replace u with ln x. and then just kind of treat these separately so we can kind of find each solution. Like, for example, take the plus sign. What does that mean? You can basically, how do you solve for x from here, right? You have a log equation, and remember that the base is e, so you can write a little hidden e there and use the property of logs, the definition. Definition tells you that, okay, x is e to the power 1 plus root 5 over 2. You could also use the e to the power both sides, because you should know that x is e to the power ln x. So if you do e to the power on both sides, you're going to get the exact same thing. By the same token, the other value, we don't really need to repeat those steps, is just going to be e to the power 1 minus 5 over 2. You got to be very careful with the log and ln, because it does not accept negative values, even 0. So we have to make sure that whatever we find is greater than 0, but take a look. In our original problem, we did have ln x, obviously, as a natural logging both sides brought us more ln's, but you have to look at the original equation, not the modified one. So we have ln x, so x needs to be positive, and x values are actually both positive. Why? Because e to the power something cannot be negative unless the exponent is complex, right? So in this case, we are good. They are both positive. Notice that 1 minus root 5 over 2 is negative, but e to the power negative doesn't mean it's negative, right? Think about it. Something to think about. Great. So that's the first method. I'm also going to show you, if I don't forget, I usually forget, but if I do, I will share the link with you. But hopefully we'll be able to take a look at this afterwards. So I'm going to go ahead and, what was I going to do next? Oh yes, second method, right? Here we go. Okay, almost forgot. Second method. So let's go ahead and rewrite the original problem, x to the power ln x equals ex. Maybe we should just talk about the domain beforehand so it doesn't become a problem later. A lot of times people will do that, but I'm not that rigorous and I'm not that careful. I make mistakes, I'm lazy, all those negative things, right? Hopefully you learn something from this experience. But anyways, so you don't have to criticize me or, kind of trash talk, because I already did it for myself. Anyways, so we have the equation, and instead of natural logging both sides, what else can I do? Okay, again, an awesome method that I like using over and over is substitution. You can do it directly. You don't have to log both sides. Let's take a look. Why don't we call ln x y this time, because last time we called it u, so we want to change it. And if ln x is equal to y, you know the drill, right? E to the power ln x is going to be e to the power y. In other words, this is x, so x is going to be e to the power y from here. That's important to take note of, because we're definitely going to use it right away. Now, here's the next step. After you do substitution, always take note, because you need to back substitute. It also helps you to see what is going on. For example, what am I going to do with x? I'm going to replace it with e to the power y. Let's do it. What about ln x? ln x is equal to y. Remember that? So I'm going to replace ln x with y. Everything is ready to go. Awesome. And then on the right-hand side, I will replace x with e to the power y again. Awesome. What does this give me? This is e to the power 1. E to the y, superpower property. E to the power y squared equals e to the power 1 plus y, because when you multiply powers with the same base, you add the exponents. Make sense? Uh-oh, this gave us the same equation, obviously, because we're solving the same problem, right? So it should come as no surprise. Now we have the following equation. Now we're going to put everything on the same side again and just solve it as a quadratic. You know the drill, but let's repeat one more time. From here, y will be, by the quadratic formula, negative b plus minus the square root of 5 over 2. And from here, we're going to get two solutions. y1 will be 1 plus root 5 over 2, and then y2 will be 1 minus root 5 over 2. Yes, y2 is negative, but we're not looking for y. And now you're like, why? Because we are looking for x, and x is e to the power y. So we're just going to do e to the power both sides, and that'll give us the x value. So we might as well just write x1 as e to the power 1 plus root 5 over 2, and x2 as e to the power 1 minus root 5 over 2. Shall we look at the solutions from alpha? Let's go ahead and take a look, because this almost brings us to the end of this video. By the way, don't forget to check out my videos on aplusbi. Here's a graph for you. Isn't that lovely? we have x to the power ln x, which is kind of exponential. Obviously, the graph of x to the x and x to the power ln x are very different. You notice that there's a minimum for this function, but no, well, actually there's a minimum for that too, but they act differently. Anyways, you get the idea. And they curve differently, but y equals ex is a linear function that goes through the origin. So they intersect as 2 points, as you can see, and those values are e to the power 1 plus root 5 over 2 and e to the power 1 minus 5 over 2. As you can see, one of them is close to 1/4. The other one is somewhere between 4 and 6, close to 5 point something, probably. I don't know. I don't have the numerical values, do I? I don't. Wolfram Alpha gave me these, so sorry, I have to share with you the exact solutions. Too bad, right? And actually, interestingly, there are complex roots as well. Where do they come from? No idea. There's probably a way to get them, but I'll leave it for aplusbi, which is my other channel, one more time. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.